Okay, hi there. So thanks so much for the really nice introduction. I'm hoping that this is going to come to life and we'll be able to see some slides. Just give me 1 second. Great. Okay, so it's a real pleasure to be here. It's a fantastic conference and really nice mix. Can I just check, because I know this is an industry day, but just to help me kind of know who's in the audience, can you raise your hand if you're actually from the games industry? Okay, and if you're actually from academia? Okay, so I don't know how many of you know this, but I started out in the games industry and then went back to academia, so I feel like I kind of cross over the two halves of the room in some sense. So it's a real pleasure to talk to you all, and it's going to be fairly high level, so I hope that there's something for everyone here, but apologies if it's either kind of too general or nothing new or whatever. But the main idea here is really to cover this ideas of reinforcement learning and what they've brought to this kind of story of the progression of games. And I've called it from AlphaGo to AlphaStar, but really there's a whole progression that this has kind of begun, and there's a huge community of people actively working on very exciting methods. And I think we're starting to see really, really interesting progress across the board in many, many different challenging games. So, why? Let's just start by going back to the beginning and ask ourselves, well, why? Why these methods? Why DeepRL? Why that particular combination amongst all the different things that we could choose to do? And so I like to think of reinforcement learning as a problem definition. So you can think of reinforcement learning, in fact, as a framework, a problem definition that describes in a very general way a huge class of problems related to decision making. So if you're interested in the science of decision making, then really RL is simply a formalization of that decision making problem, in which there's some agent which is able to actually select actions, and those actions in some way change the state of what that agent is actually encountering. So it's really, there's an agent, and what it does really matters. It changes what it's going to see next. And as a result of its actions, it will see new observations at its subsequent time steps. And as a result, there's this very challenging sequential decision-making problem where it has to choose these actions in some way so as to maximize some goal. And in RL, all we do is we formalize that goal by a single number, a scalar reward signal, and the goal is simply to select actions to maximize the future rewards. And so we just have here our familiar loop where we've kind of got going around this cycle, some agent's brain, and it's interacting with this world here, the environment, and it's seeing observations and getting rewards, and it's choosing these actions here so as to maximize those. So that's RL. So what about deep learning? Well, we can think of this as really sitting on the solution side. That deep learning is a general purpose framework for what? Well, for building representations and optimizing those representations for whatever it is we're trying to do. So if you give it some kind of objective, then deep learning has powerful methods that are able to build some kind of general purpose representation that achieves that objective that we've set it, directly from the raw inputs and with minimal domain knowledge. Okay, so the classic example would be from supervised learning, where the objective is to recognize some image and classify it as, say, a cat or a dog or whatever it is. But we can specify any objective, and the goal is for this mechanism allows it to both build representations and optimize them in such a way that it achieves that objective. So now we're going to put those together with a fairly, this should be deeply controversial. You should be challenging yourself, saying, can this be right? Can this really be true? What are we after? Well, I'm after something really ambitious, which is I want an agent that can solve any human-level task, which can do all the things that we as people can do, maybe one day even better than us. And how can we go about, that very ambitious objective? Well, the hypothesis, this conjecture, is that by putting these two things together, it may be enough. That maybe all we need to do is define very clearly this problem as a reinforcement learning problem. We specify that objective very clearly, and we set this deep learning kind of mechanism up to optimize for that objective, to build this big neural network that optimizes for that goal and achieves this objective of maximizing long-term rewards. And so the conjecture is that RL plus DL together gives us this big goal, artificial general intelligence. So of course that's a long way off, and it's a big conjecture, and maybe it's false. Maybe there's a whole set of other ingredients that we actually need to succeed. But really, you can think of this talk as exploring that conjecture by taking some first steps in the games world to see how far we can push this conjecture. Okay, so if our goal is to try and achieve AGI, well, how should we actually measure how far we've come along that path? And so for this audience, I don't really need to justify this, but again, it's good to ask ourselves, well, why games? Because games give us a really, really natural measure of artificial intelligence, like how far we've come. And if we look at both classic games like chess and Go, and video games like Atari or Starcraft, they give us really fantastic benchmarks, not just because they give us an ability to play against humans, which gives like the most obvious feature is we can now pit the AI against a human and really directly calibrate the level of intelligence of our AI against human intelligence by literally playing against each other. So it's got this fantastic calibration mechanism. But maybe even more importantly, games, they're these really clear microcosms of some aspect of the real world that's been encapsulated and designed in some way to be interesting and challenging to humans. And so whatever that aspect is of the real world that people are trying to put in there to test humans, well, we capture that, we've got very clear rules, and now we can set our AIs to try and solve that particular aspect. And games cover a huge, wide range of these different aspects of intelligence. Okay, so I'm going to go back in time a little bit and follow roughly the course that Simon mentioned in his kind introduction, and start with at the beginning with this journey with Atari. And so, this idea of Atari was really to try and, push this conjecture of trying to solve the RL problem using deep learning mechanism. And so the basic idea was to say, well, what if our general intelligence that we're trying to solve is the ability to play any Atari game? So in particular, you're provided with this Atari emulator. Well, we have no knowledge at all of what's going on inside this thing. You plug in a new cartridge and no one tells you anything about it. And that's a kind of radical departure from the way that most people have traditionally thought about AI, which is that, you specialize your system to tell it everything you can about what's inside the environment. Here we don't do that. We back off, we say, okay, we want something general, we should be able to plug anything different in there, and that generality is going to be a recurring theme throughout this talk, that the more knowledge we can take away, special case knowledge we can take away from the system, the more powerful it becomes because it's able to be applied to more and more different domains. And so all it receives then is kind of this pixels describing what's going on the screen, and some reward signal, which in the case of Atari is just the change in score. And we ask this brain to learn how to just control the raw actions on this joystick so as to maximize that score. And over here we see the particular network architecture that we initially used, which was a convolutional neural network, which is essentially processing patches of the screen and combining ever more sophisticated features through successive layers until at the end of it, it estimates a value function. And that value function is basically saying, how good is it to take one of these particular joystick actions? How much score do I expect to get if I move the joystick left versus moving the joystick right? And if you can estimate that value function correctly, well, playing optimally becomes trivial. You just pick the action with the highest value, and you'll play perfectly in whatever game it is. So the game basically becomes now figure out this value function directly from data. And that we introduced some methods to do that, known as deep Q learning, deep Q networks. And it's really essentially, for those of you who know about this, it's trying to solve the Bellman equation by Q learning, but combined with experience replay and a couple of other tricks to make it stable. So, this was just some of the initial early days of this, and we see on the left here, I don't know, can you guys see this? I guess on the left here what we're seeing is this very rapid learning actually, where it kind of starts off playing something like Breakout, which it's never seen before, and initially it just kind of starts off playing very randomly, but over time it starts to kind of figure out how to hit the ball up and knock it back. Over on the right, while we're doing that, I can just explain, huge range of different games that are being played in Atari, pseudo 3D, all kinds of different things going on, different side-scrolling, whatever, different natures, long-term rewards coming in different ways. And then eventually, we see over here on the left that after a while, it learns a strategy that none of the humans actually that programmed this thing even knew about, which is this idea that you can tunnel up. I don't know if you can see the ball even here. But you can tunnel up the left-hand side of the screen and get the ball to bounce up at the top there, and it scores very highly. And so that's kind of one of the properties of reinforcement learning, is that it's able to discover things for itself. It's able to kind of figure out knowledge that we as designers don't even know, and build that from first principles for itself in a way that enables it to achieve high performance in those domains. Okay, so that's the power of RL. So, you know, back in the day when we did this, this was the first time anyone had achieved good results in a general way in something like this, and we were able to achieve roughly human level on average across this whole suite of 57 different Atari games. And that actually opened an era of exploration when Atari became something of a benchmark for the community, and we saw people push up these results higher and higher and higher. In fact, this is somewhat out of date now. You see people getting median scores of like way over 1,000% these days. And some of the techniques which people have used, which seem to be very successful, you know, if I was to pick out the three which seem to have been most important throughout the course of all of the different things that people discover, there would be, you know, prioritizing the replays that you see, so you kind of pick out the experiences from the past that are somehow most surprising, and you learn from those the most. The idea of looking further and further ahead when you're doing your Q learning, not just to do one-step Q learning, but to kind of look n steps into the future and do Q learning from that. So n-step Q learning, and finally this idea of distributional learning seems to have been quite helpful as well, or that's kind of a third place. Okay, so lots of progress there. Reinforcement learning kind of took off with Atari. It's clearly been around for a long time. There have been success stories before, but I think this helped people to maybe see that there's a wide range of applications and capabilities for it. Okay, so the next part of the talk I want to talk about AlphaGo and just give a little bit of insight into what happened there. So AlphaGo, as Simon kindly mentioned, was the first Go program to defeat a professional player. And I feel very fortunate to actually have been involved in that story. It was something very exciting, and you know, it's something where it's just, you know, sometimes something is due. There's a time when some kind of breakthrough is going to happen, and I was lucky enough to be in the right place at the right time to be part of that. So the game of Go is very interesting to AI, partly because, you know, amongst the games which, you know, all of you guys consider, in some sense it's the canonical one, right? It was discovered, you know, thousands of years ago. The game was devised. In terms of players, the number of active players would still, you know, make most game developers rather jealous of its statistics. And in terms of the kind of search space you have to deal with, it's something, you know, very dramatically challenging for traditional AI techniques, such that all of the traditional approaches to search kind of fell over when they were faced with this kind of search space, which is just kind of very briefly illustrated here, in the sense that you have a branching factor of around 360 at the beginning of the game, and that kind of and the game lasts for maybe 200 steps, so you get this enormous branching factor of, you know, something like well, if it stayed that branching factor, it'd be 360 to the 200 throughout the game. Okay, so in order to deal with that, what was the approach that we took? Well, going back to the beginning of the talk, you won't be surprised to hear that the main approach was to combine these two ideas, to use deep learning as the mechanism and reinforcement learning to give the objective. So the deep learning looked something like this, that we had two neural networks at the heart of AlphaGo. The first of those neural networks was called the policy network, and the role of the policy network was essentially to predict the move that was chosen by the human player. Or more generally, it was just the role of the policy network was to predict a move, to suggest a move, and say, you know, with 80% probability, pick this move here on the board, and with 10% this one, and 3% this one, etc. So what happens with the policy network is it's fed in the raw description of the board, and that's processed by a deep convolutional neural network that basically processes patches of the board to devise features and makes those features ever more sophisticated, until at the end of it has a very rich representation of what's going on the board, and is able to use that to actually pick a move and say which move to actually play in the game. So that's the policy network. The second neural network, which kind of mirrors what we described in the Atari work, is a value network. It's something which is essentially looking at the position and saying, well, how good is this position? You know, if I find myself in this position, represented by this Go board, who's going to win? And so again, this thing's processed by a deep convolutional neural network, But at the end of it now, it's all gathered together into a single scalar number, which is trying to predict whether the outcome will be +1 if white wins the game or -1 if black wins the game. It's just trying to predict a number between those two things, saying, well, how good is it? Am I going to win from here, or am I going to lose? And so those two networks are at the heart of AlphaGo. And they were trained initially in the following way, and we'll talk later about how this was changed subsequently. But initially, that policy network was trained by supervised learning from human data. So in other words, it was trained directly to predict whatever move the human did in a particular position. This policy network was trained to predict exactly the same move. And so if the human, in this position plays a black stone in the corner, well, we train our policy network to also put a black stone in the corner in that position. And once that's completed, we then kind of took over with reinforcement learning. That reinforcement learning was then used to go beyond the capabilities of supervised learning. That the human data, in some sense, gives a ceiling to how well the system could perform. It's just trying to mimic what humans do. And so if it's just mimicking, first of all, it can't exceed what humans do, and secondly, it doesn't necessarily understand why it's doing what it's doing. It's just kind of copying the human without a clear understanding of why it's playing the moves that it's playing. And so for those reasons, it's super important to actually learn for itself. And the way in which it did this was to play games of self-play. In other words, from each of these positions, each position in the game, it would play a game of self-play between the policy network and itself. So it would just pick moves recommended by the policy network, play out games until the end of the game, look at who won the game, and then predict the winner. So from each of the positions, if it plays against itself, and from this position, in these games of self-play, it ends up winning the game, well, it can say, oh, well, that was a pretty good position. And if from this position it ends up losing the game, it starts thinking that's a bad position. And that gives rise to this value network. And the policy network was also adjusted by a kind of policy gradient in this work. Okay, so that was the way in which the networks were trained. This was then used to address this enormous search space that we have in the game of Go. So this is like a cartoon depiction of that kind of huge search space that you have, the kind of which in practice is really more like 360 actions from here. But here we're just looking at like a binary search tree going down a few steps. And the question is, how do we make use of those neural networks to help? And the kind of cartoon version of that looks something like this, that we first of all actually reduce the breadth with the policy network. And the way that's done is we use this policy network to kind of sample actions. So this is kind of like a Monte Carlo sampling procedure. So it's a type of Monte Carlo tree search that's used. And the sampling procedure is biased towards the suggestions that are made by the raw policy network. So that basically restricts the breadth of the search tree to just the move or the handful of moves that are considered reasonable by the policy network. And the nice thing about the nature of Monte Carlo tree search is that it slowly expands the kind of breadth over time, so eventually it covers everything. But it always kind of prefers to explore the things which the policy network considers most effective. And so that's absolutely critical to understand this, that what it's really doing is reducing the breadth of this search tree. And the second thing we can do is to reduce the depth of the search tree. And so the way we do that is more like a traditional evaluation function that you might find in like a chess program like Deep Blue or something. And the idea is that when you reach some leaf node, instead of continuing all the way to the end of the game and computing the entire subtree from that point and figuring out its minimax value, we substitute the whole of the remainder of that search with a single number, which kind of summarizes what we think would happen if we were to search to the end of the game from here. And that single number is essentially the value network. It's our prediction of who's going to win from this point onwards. And so that basically allows us to truncate and reduce the depth of the search tree. And so by combining those together, we're able to dramatically reduce the size of this search space in a principled way, which doesn't actually impose any limits and still converges on the optimal minimax solution if you were able to run this out to infinity. And so when we put this together, we were able to go and play against the 18-time world champion Lisa Doll. And this was played back in March 2016 in Seoul. And so just to place you back in that historical context, so no previous program had ever come close to defeating a human professional, and most people thought we were actually going to lose this game. And we put ourselves on the line basically just from analyzing our self-play games and some initial games we played against a kind of a kind of much weaker European player, still a professional. We had to estimate whether we were going to win this match. And I think rather naively at the time, we just thought, look at these curves, they're really going up really fast, we'll be fine. And then when we arrived in Seoul, and suddenly there were these huge banks of cameras watching us and millions of people watching online, I have to admit that I was a little bit scared as to what would actually happen in practice. And had I realized that, somehow the event was much bigger than I'd even imagined in my wildest dreams, I might have been slightly more cautious. But nevertheless, it was things seemed to go quite well. This is just a brief. It's actually a trailer from a movie, AlphaGo.
World's oldest continuously
played board game. It kind of gives you a sense of what this was like to be there.
One of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lisa Doll.
A match like no other is about to get underway in South Korea.
Lisa Doll is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The whole world is watching. Can Lisa Doll find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think that something went wrong.
Yeah, it's made a mistake.
It's got up against America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Okay, so that's just to give a little Okay, so in the end, AlphaGo won the match 4-1. There was a particular moment that I was just going to mention that was quite interesting within the game, where AlphaGo played a move which surprised all of the commentators and became like the turning point in that game. And it was such an interesting moment that maybe it's just worth mentioning this.
Ooh. That's a very surprising move.
I thought it was a mistake.
Okay, so that was where the commentators saw AlphaGo play this move in the second game, move 37, and they were so shocked by this move that they really didn't believe it was kind of a sensible move to play. And it's because in Go there's this kind of rules that humans have learned, and they've kind of followed these rules for thousands of years. That's been kind of just common sense that there's certain things you just can't do as a human or you will lose the game. And AlphaGo violated one of those rules in move 37. And I don't think you can really see this well enough, but let me just briefly describe that in the game of Go, you're trying to surround territory, and there are these lines of territory: first line, second line, third line, fourth line. And if you place a stone on the fourth line, you kind of enclose huge amounts of territory. And so you never ever want to allow your opponent to build a wall along that fourth line, because it's just giving away too much territory. And so the one thing you never do is play a diagonal stone against this, it's called a shoulder hit, against the fourth line stone here. Because if you do that, you're just encouraging your opponent to build this solid wall along this fourth line and make loads of territory. And yet, that's exactly what AlphaGo did in move 37, and it went on to win the game by actually building up a whole load of influence and encircling this large territory in the middle of the game, in the middle of the board here. And it really made people change the way they thought about the game of Go. In fact, Lisa Doll afterwards said that it changed his whole way of thinking about the game, and it meant that there were new possibilities available. And I think, again, there's something really interesting there, which is that we don't have to, we can sometimes be surprised by our machines, and if we enable them to learn for themselves, rather than learning from humans, then we can empower them to do all kinds of interesting things.
Value.
Okay. Right. So, I wanted to talk next about AlphaZero. So this was a follow-up to the match against Lee Sedol, and it was really inspired by that. It was inspired in the sense that in the match we actually lost a game, and when we lost, we realized that we lost in a way which was it was quite interesting, that AlphaGo had actually been somehow delusional for a large part of this game where it lost. It somehow found itself in a situation where it was absolutely convinced it was winning, despite completely misunderstanding everything that was going on in that game. And that actually, once we started to poke into it, we discovered that these kind of delusions happened, maybe about 1 game in 5 on average, and that somehow there was something going on which meant that it wasn't able to kind of recover from these systematic misunderstandings. And so that, led us on a search to try and understand, well, how can we overcome these delusions? What do we need to add in? Do we need to add in some more knowledge? Do we need to add in some new algorithms? And we tried a whole load of things. And of course, it came back to the fundamentals again. And you won't be surprised to hear that the solution to actually solving these was to go back to the fundamentals and use more reinforcement learning in a more principled way, and combining that in a more principled way with deep learning, rather than any kind of new ingredient that needs to be added in. Okay, and so that led to something which we called AlphaZero, which was able to play not just the game of Go, but in fact, more generally, it was able to play other board games, and we tried it on the games of chess and shogi as well. Shogi is Japanese chess. And so the features of AlphaZero, in contrast with the previous AlphaGo, were that it learned without any human data at all, solely by self-play reinforcement learning, starting completely from random. Didn't use any human features at all, so it only took the raw board as an input, whereas the original AlphaGo also had some additional features, such as tracking ladders across the board, if you're familiar with those. And finally, it's kind of fully general. As a result of these, it's applicable to many domains. So there was no special treatment for the Go board. We didn't even use things like symmetry anymore, exploit the symmetries of the Go board. Okay. So the basic idea of AlphaZero, I'm just going to take a moment to explain it, because I think it's quite interesting, the mechanism that it used, was that it basically, we trained it to use the best. So if you think of AlphaGo was taught from human experts, and that was the best possible data that we had available to train from. And in AlphaZero, we said, actually, there's a better teacher available, which is better than the human professionals that we originally trained on, and that's actually, the program itself. So what we did was we used the program itself, including all of its sophisticated search, as the teacher from which the next iteration of the program was trained. And so the way to think about this is that from each position in the game, we run one of these searches, as described earlier, using the policy network and the value network to run this very sophisticated search. And as a result of that search, we pick a move, we play that move, we run another search, we play another move using all of this search to kind of, play very accurately and precisely. We run a move, we run a search, pick a move, and so on until we reach the end of the game. And at the end of the game, we have some kind of outcome. And the nice thing is that outcome, is really high-quality stuff now. This is an outcome of AlphaGo kind of playing, with search and using all of the sophistication of learning and search together to come up with some kind of outcome. And now if we train from that outcome and these searches, we get a very rich and powerful training signal. So specifically, we generate data in this way, and then we do two things. First of all, we train the new policy network to predict the move that was actually made by the search. So what did AlphaGo actually pick in this move? Well, it ran a search, and as a result of that search, it picked this move here. So now let's train our policy network to pick that same move. And if it can do that, if our raw neural network can do the same thing that the whole of AlphaGo plus search did in its previous iteration, then we've really done something remarkable, which we've kind of shortcut all of the search. We've kind of cached all of the capabilities of something that required very sophisticated planning, and we've cached all of that planning back into the raw neural network in a way that it can just do that immediately. And so we do that, and from each of these moves we generate a target, which is the search itself, the move that was selected by search. We try and train our neural network to make the same move that the search picked. The second thing we do is we train the value network. And we train the new value network to predict the winner of this very, very accurate game. So you can think of this as a kind of policy iteration where we're actually improving the policy and we're getting this very accurate kind of new policy based on search, and we're actually using that to generate outcomes and train from them. So we train the value network specifically from each of these positions we encountered when actually playing real games of search, AlphaGo with search against AlphaGo with search. We get the winner and we update the value network to predict who will win this game, take this very accurate signal and use it to train the value network to say whether this position is good or whether this position is good or whether this position is good. Okay. And then all we do is we iterate those steps. That's the entire algorithm. We basically take those new policy and value networks and we plug those back in to the search at the next iteration. So the next iteration now uses the new policy and value network to get a more sophisticated search that's more accurate and leads to better results and so on for iteration after iteration after iteration. Okay, so we started this completely from scratch, starting from random, and it turns out it did remarkably well. That after 8 hours of training, and I should caveat that by saying this is, these numbers are 8 hours of some, very nice Google infrastructure running on tensor processing units. But after 8 hours of those, it was able to beat the original AlphaGo, the one that defeated Lee Sedol. And eventually, after it played for about 40 days, eventually it was able to win 100 games to 0 against the original AlphaGo. So the principled version, which learned from scratch just using reinforcement learning, actually significantly outperformed the version which made as much use of human data as we could put into it. Okay, and along the way, it discovered lots of human knowledge. So this figure kind of shows that as it was training, it discovered kind of all of these openings that were used by humans. So this is, at certain points, it's discovering and playing these kind of corner sequences, these opening patterns that humans took thousands of years to kind of figure out and have gradually evolved over time. But what was interesting was that subsequently it then decided that some of these weren't actually that great, and it developed its own variations that humans didn't know about, and which they now actually play in current play. So it discarded certain ones and said, I don't actually think that's so great, here's what you should do instead. And now actually a lot of humans are studying AlphaGo's games to try and change their play a little bit. Okay, so I mentioned that AlphaZero couldn't just play the game of Go, but it was more general than that. So the most natural domain to turn to was the game of chess. And the reason we looked at chess, well, chess isn't quite as complex as Go in terms of the game tree complexity, but it is the most studied domain in the history of AI, arguably. It was studied, in fact, by Babbage and Turing and Shannon and von Neumann, and it was the Drosophila, like the fruit fly, the organism that everyone studied in AI for several decades. And the reason we chose it, actually, is that in some sense it shows what happens if you do the opposite of artificial general intelligence. Because in chess, there are these highly specialized systems that have been very, very successful and very finely tuned over decades. So back in '97, Deep Blue defeated Garry Kasparov, the world champion. But actually, subsequently, there was a fantastic amount of really good research that went on, and the state of the art continued to improve massively until the point where the current programs are indisputably superhuman, and hundreds and hundreds of ELO stronger than any human player. We also looked at shogi, Japanese chess, which is much more complex than chess. In fact, it's only recently in the last couple of years that there are any programs that could play at the level of the very top humans. And it has a larger board and a larger action space than normal chess, largely because when you capture a piece, you can actually play a special move, which is to play that captured piece back down on the board as one of your own. So you kind of get to flip it over and use it yourself. And that kind of blows up the action space and makes it very rich as a game. And what's interesting is that in all of these chess variants, the state-of-the-art engines historically were based on alpha-beta search, which heavily optimized using handcrafted evaluation functions that use human experts and human grandmasters to kind of figure out exactly what the right features should be in those systems, and lots of both general search extensions that would work in any game, and also a lot of very game-specific heuristics that will only work in the particular game it's been tuned for. And so if we look at that, if we take actually 3 of the last 4 TCEC World Championships were won by this program called Stockfish. And so if we try to just open up the box and ask, well, what was inside Stockfish, we see that there's a huge set of different kind of specialized ideas, heuristics, search extensions, etc. And roughly speaking, each one of these things here would have represented, probably someone's PhD thesis or something to figure this out. And Stockfish is the most successful program because it integrates all of these, it's beautifully written, and it's kind of all of this highly specialized knowledge has been put together in one system. And so what we did was we took them all out. So we got rid of every single one of these, and we replaced it with exactly the very simple system that I described earlier, which is just this pure idea of self-play reinforcement learning, plus the kind of search algorithm which I outlined, which is in fact a self-play search, Monte Carlo tree search. And it actually did remarkably well. So after just 4 hours of training on quite a lot of Google infrastructure, it was able to beat Stockfish. And eventually, when it was trained fully, we played a 1,000-game match. And when you play high-level chess, you get a lot of draws. But amongst the wins, AlphaZero won 155 of those games, and Stockfish won just 6 of them. And the same story really was true, maybe even more so in shogi. It took just 2 hours to beat the world champion Elmo, the world champion program, and eventually we won 911 games to 77 with just a few draws. Okay. So the final project I want to talk about is AlphaStar. So this is our most recent work at DeepMind along this kind of trajectory. And this was the first program to defeat a professional Starcraft player. And this is actually ongoing work. That's, in fact, we just concluded some in the process of concluding some new tests, like this last week and this week. And so Starcraft is interesting. It's a real-time strategy game in which you collect resources, use those resources to build a base and to build units, and then amass those units to go and defeat the opponent. So it's often been described as like, chess on steroids, where you're controlling hundreds of different chess pieces simultaneously at once, and you get to dynamically adjust and build those chess pieces and get them to learn new skills. And so why Starcraft? So many people would say among video games it's considered to be at the peak of human ability. Amongst esports, this is the one which has endured 20 years of active human play. And when you ask pros, well, which is the hardest esport, a lot of them certainly choose StarCraft as like the canonical challenge amongst esports. But from a research point of view, it's also a fantastic challenge. There have been hundreds of submissions over a decade of competition. So this is actually showing the various different overlapping competitions, 3 of them in the last couple of years running side by side, where people have tried to build StarCraft bots to try and achieve this challenge. And so why is it interesting for AI? Well, it has this enormous action space. So it's a very different challenge to the kind of things we've talked about so far, because at every step, there's about 10 to the 26 actions available in our particular representation of the game, because you can send any subset of units to go and do different things, to move them around or to go and attack, and there's many different actions available with many different modifiers, and they can be sent to many different locations, and in fact, there's all of these different modifiers that leads to this kind of 13 different step sequence to even specify what one of these commands is. There's also a long planning horizon, around 15,000 steps until the game is won or lost, at which point you get a binary signal saying win or loss. And there's highly impoverished information, both in the sense that you don't get information about your opponent due to fog of war, so you only see opponent units that are within range of your own units, and you also have an active camera view, which allows you to control what you're looking at, a bit like saccading our eyes in human vision. And in addition, there's some really interesting and challenging game theory problems that StarCraft gives rise to. So it's got a non-transitive cyclic strategy space. This is really designed in from the very beginning of the design space of StarCraft, which is to say it's kind of got this rock paper scissors like cycles in the game, and it's been these have been discovered by pro players playing on Battle.net over 20 years, and the various game patches which have been applied to try and refine those dynamics to make it very fair in these cycles. And compounded with that is the fact that any one of these strategies is extremely hard to find, because there's this extremely hard exploration problem to even identify a reasonable sequence of moves that does better than what you had before. And also this kind of human alignment problem that maybe the strategies you find are only good against yourself, but aren't actually useful against humans. Okay, so that's some of the reasons to be interested in StarCraft. In practice, in this first part of what I'm going to describe, we removed this challenge. And I'll come back to it at the end because in our recent work we've put this back in, which is to say that we gave initially our agent like a full map view, so it was able to see everything on the map without having to click around it. But it was still imperfect information in the sense it didn't see the opponent units unless they were close to you. Okay, so the fog of war was still active. So this is what pro play looks like in practice. So this is, just to give some sense of what it's like to actually play this game. So this is a pro playing at several hundred actions per minute. So StarCraft's kind of famous for the difficulty of actually learning to play this game. I can't even move my fingers that quickly, and these aren't just random clicks. These really, this pro player's doing a lot of very high-level strategic decisions, chess-like in each of those individual clicks. There's an awful lot going on there. Okay. Sorry. And if we then try and convert that, again, what technique did we choose? Well, we chose, again, a combination of reinforcement learning and deep learning. So if I start by talking about, at the heart of AlphaStar was this kind of neural network, and what's going on here, sorry, it's very hard to see, it's quite a dark screen, but roughly what's going on is that this screen is being fed into the neural network in terms of raw observations, which are basically describing all of the units on the screen and all of their attributes, which are being fed into this observation thing. And this little flash here indicates the fact that it doesn't see it at every time step because we're actively choosing how often to poll this screen. We kind of choose how long to wait until we next poll this for information. That's part of the action that we choose. So we have a simple form of temporal abstraction, and that's actually really important because otherwise you just kind of get swamped by these low-level decisions. So we then receive that kind of low-level information about all of these units. That gets passed into the neural network. I'm not going to talk a lot about the architecture except to say that it's very heavy on attention. So we have kind of recurrent neural network that helps us deal with an LSTM that helps us deal with all of the partially observed aspects of the game to kind of remember all of the things you've seen about the opponent in the past. And that LSTM accumulates together, but we have this attention mechanism that allows it to kind of focus on different units and decide which units are actually relevant at any moment in time. So this attention mechanism says, okay, I want to look at what this unit is doing and this unit and combine those together into some feature, and then look at this unit and combine those together into another feature. And that's all pulled together into this big LSTM, and then the output of that LSTM goes into the next part of the network, which is selecting actions. And the actions are kind of selected autoregressively, which means kind of step by step. And in fact, as I mentioned, there are many, many steps to this action construction process, some of which are shown here. But first of all, it kind of picks which kind of action it's going to do. Like, is it going to move or attack or build? And that's this kind of, you can sort of see its probability distribution here. It's deciding which of these things to pick over. And once it's decided which of those to do, it starts to choose the modifiers for that. In particular, it chooses which location it's going to apply that thing to. It also has attention over the different units that's going to be applied to. It kind of picks a sequence of units that action is going to be applied to. And finally, we have a value function that gets predicted as well from the same neural network. Although this value network actually receives, during training only, not when we're actually playing, this thing doesn't cheat, but during training only, this thing also receives information about the opponent's units, and that helps us to reduce variance by kind of having this kind of additional knowledge that's in this estimate of how well you're doing. Okay, so that's the sort of anatomy of what's going into StarCraft. And you see it's a very rich and complicated thing, which hopefully is a step towards some of the architectures which we might need for larger applications in the real world. So the way we trained this thing was by introducing something called the League, the AlphaStar League. And so this was, roughly speaking, a multi-agent reinforcement learning algorithm. So this is multi-agent at its heart because we're trying to deal with all of these game theoretic aspects and these kind of cycles that you get in the game space and this very hard exploration problem of how do you even cover this strategy space when you're unlikely to ever even discover the sequence of actions that leads you to build some sophisticated units. And the way that we do that is by having a diverse mixture of opponents represented in the league, and I'll describe how we get that diversity shortly. And we train our agents, by reinforcement learning, by act-critic reinforcement learning, to defeat that diverse mixture of opponents. So roughly speaking, the agents in the league are trying to defeat not just themselves, but a whole range of different strategies which are simultaneously represented in this league. And that makes them much more robust against all of the different kind of ideas that the opponent might try, all of the different cheeses or all-ins, if you like, that the opponent can try, or the many, many different strategies. And the mechanism that we use is not based on naive self-play, because naive self-play in this kind of situation where you have imperfect information, it's well known that naive self-play just tends to cycle and forget the strategies that it used to know about. So it kind of gets stuck in this cycle of learning to beat itself, and then learning to beat that self, and then learning to beat that self, and before you know it, it's forgotten how it beat the original one. And so what we used instead is a variant of fictitious play that we introduced called prioritized fictitious play. And the main idea is to play the opponents in the league in proportion to their win rate against the agent. In other words, all the agents that are successful against us, they're the ones that it's most important we learn how to beat. If we're already beating an agent 99% of the time, we really don't want to play it very often. And this also ensures that the agent doesn't forget its old strategies that it had before, because if it ever forgets how to defeat a particular opponent, that opponent will suddenly be selected a lot and played a lot, and it'll kind of come back to life, and it will have to learn and make sure that it can still defeat that opponent. So this kind of guarantees that we have this sort of non-forgetting property. And furthermore, we then have these diversity mechanisms where the agents are encouraged to play against a wide diversity of counter strategies. And this happens in two different ways. First of all, diversity comes by having some of the agents in the league specialized to play only against particular agents. So we call these exploiters. They're learning how to beat particular agents in the league. And when we kind of train these particular counter strategies that might not themselves be robust, but are very, very good at finding the weaknesses in our agents. And so if we're able to defeat those exploiters, our agents are able to address their own fallibilities. They can address their own weaknesses. And in addition, we have some agents which are incentivized by pseudo-rewards to play in particular ways, and I'll talk about that next. So unlike AlphaGo Zero, we actually did make use of human data in Starcraft. And the reason that we did this was really to try and cover this very large strategy space that for now, I would love to see a method which doesn't use human data, by the way, but for now, the way that we were able to get past this hard exploration problem was by making use of what humans do in three different ways. So first of all, we trained initially from supervised learning, and that enabled us to cover the modes of human-like behavior. So these are modes which we may be extremely improbable to ever encounter in practice, but if we look at the modes of human behavior, they kind of give a nice set of kind of starting points for our agent to begin from. The second thing we did was we added a term to our reinforcement learning, so even once we then continue with reinforcement learning, so we sort of start off by initializing from the supervised learning, but then even beyond that point, we make sure that we don't go too far away from what the humans do. So we basically train it to stay close to these modes of human-like behavior. And thirdly, we have an additional incentive, which is given by pseudo-rewards. So what does our RL try and do? Well, it tries to maximize the game outcome, +1 for winning, -1 for losing, plus some pseudo-rewards. And those pseudo-rewards basically encourage the policy to stay close to the human build order. So what we do is we pick a game that the humans played, we look at the opening that human used, and then we introduce a penalty if the RL actually deviates from that human opening. And that encourages it to cover the whole spread of different things that humans do, and explore those, but to find its own ways to play with respect to those human openings. Okay, so when we put that together, it looks something like this. We call this the AlphaStar League, and roughly speaking, we start off with our supervised learning, and then we have a whole bunch of different agents which are playing by reinforcement learning, and our main agents just play and play and play against all of these opponents, trying to defeat them, but the other agents periodically reset. That's what these little arrows mean here, that every now and then they just get reset, again to encourage diversity. They get reset to the human data and they try a different thing, and then they get reset and they try a different thing. And these exploiters are just trying to kind of find the holes in what our other agents are doing, and that gives us a nice diversity in what's present within this league. Okay, So this figure here shows the progression of our agents over time. So this is during supervised learning, and then this is when we start our reinforcement learning, and this is the number of days we train for, and this is a kind of ELO rating that's actually used by Blizzard when they devised the online ladder for Starcraft called Battle.net. They use this rating system called MMR, and this shows our progression in our estimated internal MMR relative to the 2 players that we selected to actually play against, which were 2 professional players called TLO and Mana. And so you can see, according to our internal estimate, we were doing quite well. And the question is, how well will we actually do when we played against them in practice? But just before I go there, this is one figure I think is quite important to look at, which is whether we really had achieved our goal of stable training in the presence of these kind of cycles that you get in the game. And what this shows is the progression of training over time. So this is each successive iteration of the AlphaStar League against, and then what we look at is basically we ask the question, amongst the agents that we have at each iteration, which one of those are dominating the pool of strategies? And we do that by computing a Nash equilibrium over those particular strategies that are in the pool at that time. And these kind of little blobs here are representing that Nash equilibrium. And so let's just forget about the details. Roughly what this is saying is that the only strategies you would ever choose to use at, say, this point in time are the ones which are represented in this blob here and maybe a little bit back here. You would never choose, so these are the successive iterations going down here. So if we look at one of these, if we look at, say, this iteration along here, you would only ever choose to use your most recent blob of strategies and a little bit that goes back in time to here. But you would never ever choose to use any of these strategies that came before. They've been completely dominated, which means you don't need them anymore. So this is basically telling us that the frontier of the system is continuing to progress monotonically and get better and better and better over time during training. This plot is just kind of showing the sort of unit composition that you have in the game, and it's showing how one of our agents that we actually trained kind of moves around, one of our main agents moves around in strategy space as it discovers kind of new things and plays against different agents in the league. It's kind of encouraged to kind of discover new things and figures out a whole new kind of composition of units to play. And this one, a little bit embarrassingly, is us watching as we played against these pro players for the first time ever, and this is us making fools of ourselves as we got rather excited about what happened.
I haven't really seen a pro play StarCraft up close. The 800 clicks per minute. I don't understand how
So this is TLO. He was the first pro that we played against.
Useful clicks.
After the first match, I knew now it was on.
Okay, so that was the very first time that we defeated a human professional player in the game of StarCraft. But we went on to actually win 5-0 against TLO, who's a top 6. So he was actually playing his off race. We asked him to play Protoss, which was the only race that we trained at this point. And he's a top 16 player in North American League, roughly speaking. We defeated him 5-0. But then we played a stronger opponent playing his on race, like his own race of Protoss. So this is probably one of the top 3 or 4 Protoss players in the world. And we defeated him 5-0 initially, and then we played one live match, which was under different conditions, and we actually lost that match. And I want to just return to that because that's the interesting one. Because that match, we actually returned to our initial challenge that we'd got rid of, which was that we'd removed this camera view. And what we tried in that live match was to put the camera view back in, to actually have specific actions where you have an action now which is to move your camera and look at something, and you only receive you only can receive information about what's on your camera, and you can only do certain actions regarding what's within that camera region. And so it's kind of putting a version of the camera view back into the game. And so we lost that game, and so that encouraged us to continue. And so, really, this brings us right up to the present day, because over the last week or two, we've actually been playing online on Battle.net, which is the online ladder, against strong human players in the full game of StarCraft. And so this is really quite different to what we did before, not just the camera view, that we're now playing all races against all races. So that's actually 9 different race matchups, or 16 different race matchups if you include the possibility of playing random. And we're playing on all the ladder maps that humans play on the, under the same conditions that humans play on BattleNet. And we also have much stronger restrictions on the interface that we're allowed to use. So we had some consultation with pros after the last game, and they said we were still clicking too fast in the last game. And so we've restricted it further. And in addition, we're playing a single neural network per race now, so it's kind of more elegant algorithm. And so, I can't give final results because it's still concluding, and we're playing online as I speak. We've just been finishing this off in the last couple of days. But results look very promising. We've had some really nice feedback from pro players who think that we're playing, in a really nice way. We've had some fantastic games against some of the top grandmasters in the world for all of these different strategies for all of the different races. Okay, so just to finish, of course, we all care about games. This is a conference about games. But I think it's really important to maintain that link between what we do in games and what matters in the real world. We do games because they're fun, because they're great test beds for AI, but also because we believe that what happens in games has consequence to the real world. And so I just wanted to mention that one thing we tried in DeepMind was this work called AlphaFold. And this was really trying to tackle one of the world's most important open problems for science, which is the problem of protein folding. Which is where you have some kind of protein structure which is given to you, and actually the function of a protein is determined entirely by the form which it takes when it folds up, and that determines what it really does when it's actually in the body. And so if we can understand and predict what structure it will take, what it will fold into, then we'll be able to design new drugs and solve all kinds of interesting problems for science. And so this is a huge open problem that's been active area of research for years. And what a team did in DeepMind, what we looked at was trying to apply, there was less of the reinforcement learning, but it still took some of the same ideas of building a very sophisticated deep learning system with a sophisticated neural network and combining that with a kind of search. In this case, it was based on simulated annealing, and some of the results I'll show you, and combining those together to get some state-of-the-art results. And so this plot here, just very briefly, I don't have time to describe it in detail, except to show that this was the biennial assessment. This happens every 2 years where all of the top teams in the world compare their protein folding systems. And each of these green lines is one of the other systems in the world. And this blue line is actually the assessment which was performed by this CASP13 group to decide how well the systems were doing. And this was the DeepMind system, kind of significantly exceeding it. And this is in particular proteins and looking at how we actually learn to fold it. And again, the DeepMind system was way ahead of some of these other systems in many of those proteins. Okay, so there's some resources here if anyone wants to look at any of these things in more detail. There'll be a paper coming very soon on AlphaStar. We're just submitting that at the moment. And thanks very much for listening.
Thanks for an excellent keynote. Do you have a microphone, please? So we just have a couple of minutes for questions. Anybody want to go first? I see Peter with his hand up there. We get a microphone to Peter, please.
Hi, Peter Cowling from the University of York. David, amazing talk. Wow, I wish I had your resources. For problems which can be categorized as problems, for functions, I can see that the techniques that you describe may get around to solving many of those problems. But most of the things that make life actually worthwhile aren't easily categorized as functions. Yeah, falling in love, or being, or understanding, the joy of victory. Can you talk about progress in those sorts of areas?
So that's a great question. So I should be more precise in what my goals are for artificial intelligence. So when I talk about artificial general intelligence, the goal is more specific, which is to be able to achieve human level of performance in the kind of environments that humans are able to succeed in. So if we define specifically our problem, as, can we get a system which can, achieve whatever it is we want it to achieve in terms of numerical reward maximization in a wide range of different environments, then it falls exactly into this kind of framework that I've described. If you're talking about things which fall outside of that, I don't want to begin to speculate, honestly, as to, I'm not trying to claim that this covers the subjective aspects of human life that we all care about and enjoy from day to day. It isn't about that. This is about specifically human capabilities with respect to their intelligence and how it leads to performance in succeeding at specific problems, or generally at problems.
Super. Question there, Dan. Can we get a microphone to there, please?
So I'm going to try and land right on the boundary of the last question in your presentation. Can your AI think up fun new games? That was something I didn't see.
Sorry, it's a bit hard to hear with the tube. Did you say, can
your AI think up new games that are amusing, that are fun?
So that's a great question too. Right now, we haven't gone down that path at all. I think it's a great. I'm sure that people in this room, I really encourage you to try it. Things like this. I think the real challenge is defining fun. Like, how do you define and measure fun? If you can come up with a metric which is really encapsulating that, sure, I think we have techniques which are able to make progress towards it. But the challenge is in coming up with a reasonable metric.
So unfortunately, we have time for only one more question, and that's going to be Alex.
Hey, Alex Whittaker, Bossa Studios. Thanks, Dave, for interesting presentation. Nobody likes getting beaten hollow when playing games. Do you think you could train your systems to only just lose?
So I think the hard part of the problem is actually being able to win at all. And once you can win, I think actually it's much easier to calibrate your system to introduce weaknesses. Now, whether those weaknesses are satisfying to humans in the way that they lose is a different question. But it's, typically, you look at the history of computer chess. Once people were able to beat humans at chess, it was relatively easy to scale back the level of the AI to a certain level. And restrict its search, restrict the size of the neural network, whatever it is. We could calibrate it. Now, you want something more than that, which I think. So there's two problems then. One is can you do it dynamically, so it's kind of just losing or just winning every game. That's kind of interesting. There are methods that people have looked at, like dynamic Comey, things like that. I'm thinking of in the game of Go would be dynamically adjusting the rules of the game so that you're trying to win by a greater or lesser margin, depending as it adjusts. So that might be one idea. I think the other part of the challenge is to do it in a way that humans find interesting. Like, you could calibrate it just by resigning at the beginning of every, third game, and maybe that calibrates it back to the right level, but it'd be not very exciting for the human to play against. So playing badly in a way which is meaningful to humans is also an interesting problem.
We're out of time there, so let's thank David again for a fantastic keynote. Thank you.